Hey everyone, uh, and this particular video I'm making uh, because I want the audience to understand the kind of impact a convolution of a impulse response is going to have on the nature of frequency response of any signal. Okay, so you can see here, this is my screen that's being recorded. So let me run this particular first command. Okay, I hope everybody have increased the font size. I hope it's visible. So rank 1 comma 10,000 minus zero point 0.5. What this does, let me run this piece. Okay. So this will be my test data. Now, can you see this particular thing? So it's a random noise, 10,000 samples, value spread evenly from minus zero point 0.5 to plus zero point 0.5. Okay. So this is a data because you never know, right, what kind of data you're sending, but this will be our test data. Why we are choosing this particular data is because its frequency response is also interesting. Okay. See, I will use FFT very casually. See here, fast Fourier transform of that particular noise. Let me plot this. I'm plotting only the absolute value. Okay. So here it is. Its frequency response is also quite interesting and it's useful tool for us to analyze the performance of any filters because it spans from entire range of frequencies. Okay, so we will take only up to it's 10,000 points, right? We will refer only from 0 to 5,000. Afterward, it's a replica, okay, which is the LHS on your textbook. Okay, so let us get started. So see here, I have chosen, this is my first impulse response. I will call it as, I have called it as L5 for some reason. It has how many values? 1, 2, 3, 4, 5, 6 values. If at all you plot this impulse response, 1 at 0, 1, 1, 2, 3, 4, and 5. Okay. Other than the first sample, which is there at 0, it is referring to 5 previous samples. Whereas the second one is L3. Okay. This one you can see, other than the first sample, it is referring to this is 0th one, first one, second one, and third one. It has 4 samples. Then there is one more H5. It has how many samples? 1, 2, 3, 4, 5, 6, and 7. Even though this is a 0, it still counts, okay, for some reason, which I will explain to you in the class. Then there is H3, which is only 3 sample wide. Then there is B5, and there is one R5. Their length is somewhat larger. Okay. You can see their length is somewhat more. Okay. And did you observe an interesting thing here? All these impulse responses, H of n's, all these impulse responses are symmetric in nature. You can see 0.433, 0.065, 645, and minus 0.0078 on the left side. And on the right side, you can see the left half and the right half, not from the midpoint. Okay, from the midpoint. See here, this is a odd value. So except the midpoint, values on the left and values on the right of the midpoint, they match here also. Okay, that's a common point. Okay, it has a strange implication or observation which we'll have in our regular class. Anyway, now what I will do is this particular video is a prelude to what we are going to get into, which is filters. Okay, so what I am going to do is I have taken this particular x, the random noise. I am simply going to convolve my x, not me, you. Okay, that's what you are going to do in your very next lab after you see this particular video. You're going to take that particular random noise and you're going to take each of this. You're going to start with this particular L5, then L3, then H5, then H3, then B5, then R5. You are going to convolve your random noise, which will be your data eventually. And then you are going to observe the frequency response. Then you are going to observe the frequency response of them along with the frequency response or along with the, sorry. You are going to observe the frequency response of the convoluted data, which here XL5 along with the original data. Okay, shall we? Shall we? Now let me run this command. All the impulse responses are initiated once. Okay. See here. Let me run this. You go to type this. Okay. Then afterwards, okay, this is the let me close it. Okay, let me close all other images that are open. Now what I will do, I will convolve this. Okay, let me convolve. So if at all you see the time domain, you cannot make any sense out of it. Time domain is like that. Okay, too many samples, no even analysis coming. Now here, see what I will do now. Once again, I will plot the Fourier transform of X, the original random noise. Once again for you, there it is. Okay, this is the random thing. This is a frequency spectrum, by the way. This is not a time domain signal. X-axis is frequency, y-axis is magnitude at a particular frequency. This is a frequency response. You might have seen, in your analog communication class, the responses, the spectrums being drawn, or in your filters, right? Which you did in your communication lab, right? A second order filter, first order filter. That's what it is. X-axis is the frequency, y-axis is the response magnitude at that particular frequency. Now, once again, okay, let this figure be on. Then I will use a hold on. There you go. And then afterwards, I will plot the frequency response of the convoluted data, right? See here, convolution, simple convolution, which you did in your basic signal processing. Okay. And you can see here, boom, what has happened? This is the original frequency response. You can see in this particular new frequency response, all the lower frequencies have been allowed, and the higher frequencies, as and when the frequency reaches, see, what did I tell you? Only up to 5,000 you observe. The rest of the thing is a replica. Up to 4,000, okay. You can see as and when the frequencies increase, the strength of the signal, okay, for that particular frequency goes on reducing, right? Okay. Now let me do this. Okay. So now let me tell you what you are supposed to do. You are supposed to make these observations. Okay. You just observe these things and have fun. Okay. Now let me try something like this B5. Let me try something like B5. For that, what I will do, I will just name this as B5. But here, this is the thing. I will use the response, impulse response B5, and I will convolute it X. Okay. Now let me run it. Okay. Here you go. Now did you observe? Right. All the lower frequencies are suppressed, higher frequencies are suppressed, and in the center, few set of frequencies are being allowed. Isn't that cool? Right. So the earlier thing that we saw, it was a low pass filter, right? Same textbook style. And this one, what we see is a band pass filter. Okay, it's a low pass filter and a band pass filter. Okay, so what sort of filters will be there? Now see here, this particular thing, one current value, h of 0, then 1, 2, 3, 4, 5. Since it referred other than current value, 5 previous values, this will be my fifth order filter. And here, since it referred 1, 2, 3 previous values as compared to the current value, it's going to be my third order filter. Okay. Then there is why the names. This one here is a low pass filter. These two are high pass filters. This one is a band pass filter. This one is a band reject filter, right? The terminology sounds interesting, right? Wiki, and observe. Okay. And one more thing, what I want you guys to do is, after having this particular observation, I want to go on changing all these values and observe, make your own observation, and I will interact with you in the class. One more thing I want you guys to do is simply type in freqz, which is a ready command for plotting the frequency response, and type in the name of the impulse response. See here, I will start with L5. Okay. Now let me select this. Right click, evaluate selection. Okay. Yeah, there. This is the frequency response. Earlier, what we saw was the frequency response of the resulting signal. Okay. After convolution. This one here is the frequency response of the impulse response, right? What is the frequency response of an impulse response? Frequency response of a signal x of n, h of n is the discrete time Fourier transform of h of n. Okay, that's what a frequency response is. Now, what does it tell you? This tells that this is a filter wherein you are going to get a filter wherein all lower frequencies are going to be allowed. Then as and when frequencies go on increasing, the magnitudes are going to get suppressed, right? You know our classes, how it works, right? You have a class at 9. So we start at 9 o'clock, students come in, we allow 9:05, 9:06 or 9:07. After 9:10, we don't allow students outside, right? So that's a high pass filter, right? Okay, okay. So see something here. Okay, stupid example. Okay. So similarly, now that was L5, and then there is L3, right? That's the other one. Now let me execute that L3. L3, let me execute. Okay. This is L3. Earlier one was L5. Did you observe any change between L5 and L3? L5 is a fifth order filter. L3 is a third order filter. What's the change? They both look similar, right? Well, you got to do it. Okay. Let us see what sort of observation you will come with. Similarly, let me type in R5. Let me type in a R5 and observe what is happening. Okay. Let me type in R5 and see what is happening. Ah, there is something strange, right? Something strange. Okay. So that's it. That's your activity for the next class immediately when I send you this particular video. Okay. So let me stop here only. Bye.